So in class, we've been looking at how we can determine the rate law when we're looking at the concentration versus time. And as we discussed, the rate of a reaction can be determined with our rate law, as shown on the right. And we also talked about at the beginning of the unit where my rate can be equal to the change in concentration of A over time. Well, if we take these two cases, and we know that in both cases I calculate rate, I could make them equal to each other and then perform an integrated rate law. And with this would help me to determine the rate law for a reaction. So what we're going to do is we're going to look at them in terms of a variety of values of m, where m can be 0, 1, or 2. And then we're going to combine these two reactions and manipulate them so that we get an equation that is in our y equals mx plus b format. We'll look at the graph of what this would be, and more importantly, we'll look at the slope. So if m were to equal 0, then my two equations would be equal to each other. And on the left-hand side, concentration of A would be to the power of 0, and so it would go away. And so K would be equal to change in concentration over A over change in time. So if we manipulate this, we're left with the concentration of A at some time t is equal to the initial concentration of A minus KT. And so if we were to plot a graph of concentration versus time, more importantly, then it would be a straight line graph. And so therefore, if we looked at this the other way, if I performed an experiment and I collected concentration versus time data, then what I could get is if I have a straight line graph, it would tell me that m is equal to 0. Additionally, the slope of this graph, because we're in our y is equal to mx plus b format, the slope of this graph is negative k. And so this graph would also allow me to determine my rate law constant. Well, what if we have this graph and I plot my concentration versus time? We now know that tells me that m is equal to 0. But what if I plot my concentration versus time and it's not a straight graph but a curve? What that tells me is m equals 0. So the plotting of a concentration versus time graph tells me one thing. It tells me m is equal to 0 or m does not equal to 0. And so if I get a straight line graph for this graph, I'm done. I can stop. If I don't, I get a curve, then what that means is I have to plot subsequent graph. And so in this case, what I would plot is the natural logarithm, or the ln of concentration versus time. And if I were to plot this graph and get a straight line, then what that would tell me is that m is equal to 1. And so here we can see what our graph looks like. And this comes about through some calculus, and we're not at all interested in how we go from the combination of the two equations to our final equation in our y equals mx plus b format. But more importantly, we're just interested in what the graph looks like and what it tells us. So therefore, again, if I plot a ln of concentration versus time, and it's a straight line, that tells me m is equal to 1. And again, my slope is equal to negative k. So we can see here again, if we plot our ln of concentration of A versus time, if it's a straight line, m is equal to 1. But if it's not a straight line, and we can see in a graph on the right that it's not straight, I've plotted a straight line and we can see that the separation distance between the points changes and it has a curve to it. All that tells us is m does not equal 1. And so therefore, if we had plotted our ln of concentration versus time and not had a straight line, then we have to plot a third graph. And the third graph that we would use to determine the value of m is the inverse of concentration versus time. And again, if we set our two equations with each other again, the math to get to our y is equal to mx plus b format. We're not interested in. All we're interested in is being able to interpret the graphs. So if I plot my inverse of concentration versus time, and it's a straight line, what that tells me is m is equal to 2. So, how does this help us? And how does knowing these graphs help us? Well, if I had a concentration versus time data, and this concentration versus time data could come about in one of two fashions. I could set up a series of trials with different initial concentrations and measure the time until some change occurs, for example, color change. Or I could monitor the concentration of my reactant over time. Either way would give me concentration versus time data. I would then take this and I would first plot a concentration versus time graph. And I have my two possible outcomes. If I get a straight line, I know m is equal to 0, and I'm done. I don't have to draw any more graphs. If it's a curved line, then that tells me m does not equal 0, and so as a result, I have to plot a second graph. And so now I'd plot the log of concentration versus time. If this graph turns out to be a straight line, then I'm done. And I know that m is equal to 1. If this graph turns out to be a curved line, then it tells me that m does not equal 1. Now we have to be careful when we do this, because if I tried to plot the log of concentration versus time right away, and I got a straight line, then m could be 0 or 1. And I only know that it's 1 in this case because I've already shown that it does not equal 0 with my first graph of concentration versus time. Now, if I see that I have a curve and I'm going to say that m does not equal 1, then what would happen is I would have to plot a third graph. And I would plot the inverse of concentration versus time. And if I got a straight line here, I would know that m is equal to 2. Now, for the cases that we're going to deal with, our m values, if we're determining them graphically, will only be 0, 1, or 2. We will not go past 2. Okay, so in best case scenario, we plot one graph. In worst case scenario, we have to plot 3 graphs. But we have to plot each of them to be able to effectively determine the value of m for my rate law.